So my task is to talk about Lambda CDM model, its current status, and the future prospects. All right, this is. I'm sorry. That's it. All right. So, so what is Lambda CDM model and how do we measure it? How do we test it? First of all, we can test it by using cosmological observations, and in particular, the two I'll focus on is cosmic background anisotropies and the large-scale structure of the universe. But what is the model itself? Well, we have a kind of standard model of Lambda CDM, which is defined first by initial conditions. We think initial conditions are set by inflation, and in the simplest model of inflation, the inflation sets the amplitude of fluctuations and the slope of fluctuations, and also sets the amplitude of gravitational waves, which we describe with so-called tensor to scalar ratio R. Then a couple of other parameters that are there, and we're not really. I mean, they have a value, but we're not really interested so much in their origins. For example, the expansion rate, the matter density, the cosmological density, but there is also the curvature of the universe, which inflation predicts to be 0, and in that case, the matter density and the dark energy density are not independent, but they add up to 1 in the units of the critical density. So in total, and finally, we have a baryon density. So in total, we have about 5 to 7 free parameters that define the standard Lambda CDM model. So there are many different extensions that are possible. I'm sure we'll talk and hear a lot about them in this meeting. But so far, I think it's fair to say that there's no evidence for any of these extensions to have been detected. Examples are, for example, dark energy equation of state that is different from the cosmological constant, neutrino mass that is different from the standard prediction, non-standard inflation, alternatives to inflation, perhaps, and so on. Okay, so let's start by talking about the neoclassical tests, basically how we probe Lambda CDM. One way is to look at the redshift distance relation, which already goes back, of course, to Hubble and his way of doing it. Okay, so that's this plot here. He got it wrong, the slope. He got wrong the slope by a factor of 10, and I'll come back to this. This is the famous Hubble constant question. But even if you don't know the absolute normalization of the slope, you can still probe things like how this redshift distance relation is changing with redshift. And this is, in fact, how the first time cosmological constant or dark energy has been detected using the supernovae. Okay, so let me talk about one specific probe, which is also a standard ruler, which is baryonic acoustic oscillations. The physics of this is that we have baryons and photons in the early universe are tightly coupled into so-called baryon photon plasma, which supports pressure waves. And here's an example of this. As we launch the pressure wave from the Big Bang, in the dark matter will be doing its own thing, but the photons and baryons will be actually tightly coupled, and they will launch a pressure wave. This pressure wave then stalls after recombination, roughly at around 1000 redshift, and then we have a correlation at roughly a fixed distance of 147 megaparsecs. Okay, so that's the basic picture of this. Let's skip this. And how do we observe this? We observe this by looking at the correlations in the galaxies, for example, and we can look at the correlation function or the power spectrum. In the power spectrum, we see these characteristic oscillations. In the correlation function, we see the bump at, as I said, roughly 147 megaparsecs, which in H inverse megaparsec units becomes roughly 100. Okay, so that's the idea. But there's a third way that recently finally started yielding the results, which is instead of looking at the acoustic horizon that I just described using baryonic acoustic oscillations, we can also, there's another distance that is determined by matter radiation equality. So basically by the ratio of the densities between matter and radiation. this is the thing that defines, for example, where the power spectrum peaks. It's a very weak function of scale, but nevertheless, it can be measured. And recent results from ACT measurement have focused on that specific test as opposed to using baryonic acoustic oscillations. And one thing that's quite interesting is that the degeneracies in this omega matter H0 plane are different. For example, the BAO would give you this kind of degeneracy, but this one, matter radiation equality, is giving you this kind of degeneracy in this plane. So ACT has observed this measurement here. You see, it's roughly I don't know, it's 66 or 67. In very much consistent with the Planck data. And then we have two of these direct distance ladder measurements, one based on Cepheid calibration, one based on the tip of the red giant branch. And you can see that there's good agreement with this one, but maybe not with this one. All right, let me show this plot one more time. So here is a compilation of most of these measurements. And there's a pretty much a good consensus. So this is Planck data, roughly at 67, 68. And actually not just Planck data, all of the CM data are kind of consistent with each other. SPT, ACT, WMAP, all of them. This is this new measurement that I mentioned that doesn't use the BAO, the acoustic horizon scale, and actually gives the Hubble parameter is actually even lower than this. And then we have this direct distance ladder, which depend on this calibration problem. And tip of the red giant branch is consistent, as I shown in the previous slide as well. But Cepheid calibration is not. And also notice the Cepheid calibration, that the authors of this, they assign a very small error. Okay, so and finally, there is this strong lensing signal, which still has a lot of modeling issues. There's something called mass sheet degeneracy that makes it somewhat model dependent, and this is reflected therefore by the fact that this has pretty large, not just statistical errors, but also systematic errors. Okay, so the bottom line here is, I would say, all of these measurements are consistent with each other with the exception of the Cepheid calibration, okay? So, all right, so let's move on. Now, what about initial conditions? Inflation sets the initial conditions if we believe in inflation. And the simplest model of inflation predicts, first of all, nearly scale invariant power spectrum. This is codified in this NS slope to be close to 1. Then it predicts subdominant gravity waves. This is codified in this R coefficient, gravity wave to standard fluctuation ratio, which is supposed to be less than 1. Fluctuations are supposed to be nearly Gaussian, adiabatic, and spatially flat. Okay, so there are open questions, which is, what is the energy scale of inflation? How far did the inflaton field travel, and how did inflation begin? Some of these can be observed, can be actually answered by these kind of questions. Sorry, by these kind of measurements, such as the slope and tensor to scalar ratio. So, what can we measure in terms of probing inflation? We can measure the slope of density fluctuations. And the best probe for that is combining cosmic microwave background and large-scale structure, because we have a much larger leverage arm in that case. Then we can measure the tensor to scalar ratio. This is this R, and the best way to probe this is B mode polarization of CMB. And then finally, primordial non-gaussianity can also be a test of inflation. And the best probe currently is cosmic microwave background, but we expect that in the future this will be actually large-scale structure. So B modes are something something that we can observe from the cosmic microwave background anisotropies. They have this kind of pattern where under reflection in the mirror, they change the sign. And there's actually several different regimes of these B modes. For example, there's this what we call reionization bump on very, very large scales. This is very difficult to measure due to the foregrounds from our galaxy. Then we have this recombination bump, and this is around L of 100. This is what most experiments are focusing on these days. And then on top of that, actually, we also have B modes from lensing, which, depending on how you look at it, it's either contamination to the primordial B mode, or it's actually a very important signal on its own. And I'll get back to this, how important the signal is on its own, and how I believe that in the future, this signal here is actually going to be our best probe of large-scale structure. So there's a lot of experiments of the CMB. There are from the ground, from space. There's obviously Planck NW map that already happened. In the future, there will be light bird as well. There are experiments from South Pole, such as SPT and Bicep Keck, and there are experiments from Atacama Desert, such as Acton and Simons Observatory. So where are we right now in terms of inflation? The current limit on R is roughly 0.06. This would be the limits, and the current measurement of NS is roughly 0.96 and something, right? So these are the limits right now. And these are already probing and ruling out several of these inflationary models. For example, the power law model, this one here, is essentially, you know, okay, there's maybe touching to sigma here, but essentially almost ruled out. And also many other models, they're going to be pushed by these measurements. So if we actually end up zooming in, so this is a prediction how our measurements are going to come down from this 0.06 now. In the future, maybe we'll reach 10 to the minus 4. I'm not sure, but you know, probably we'll reach 10 to the minus 3. And these are many different models here that are just giving you a flavor of how this is going to be testing various models of inflation. Okay, what are we actually testing is the shape of the potential. You know, we already know by these measurements that the shape of potential is not something simple like a power law, right? So maybe we need an inflection point and things like that. And so it's going to be interesting how this maps then to the models of inflation. All right, so let me now switch gears to talk about the other tension, which is the amplitude of fluctuations at let's say low redshift, which is what large-scale structure probes, versus high redshift, which is what cosmic background probes. Okay, so there have been many claims in the literature, in recent literature, that large-scale structure amplitude is lower than the cosmic microbackground isotropies, and the question is, you know, is this real or not, and what's the current status? Okay, and the two main probes for in this are weak lensing and galaxy clustering, in particular galaxy redshift space distortions. So let me describe. Okay, so how does this go? So basically, after the recombination, the structure grows in time due to gravity, and we have several probes along the redshift. For example, there's Lyman alpha Forest, which probes at higher redshift 2 to 4. I already mentioned CMB. Then we have weak lensing, which probes roughly redshift below 2, and galaxy clustering, which also probes roughly below 2. And so this is the equation that governs it, right? But the main thing that controls it is basically the density initial amplitude fluctuations, but also matter density and Hubble parameter and so on. So there are a lot of different effects that can affect how the structure is growing in time. So weak lensing of the galaxies, basically the idea here is that you have some intrinsic shape of the galaxies, but as the light propagates through the universe, is being distorted by intervening dark matter or total matter, and it gets distorted into some kind of elliptical shape. Okay, so if it starts, even if they all start circular, they get distorted in this kind of form. All right, so this is due to, and in projection, this would look something like this. It's essentially a map of projected total matter density. That's what we can measure. So how does this then translate into parameters? Well, it's sensitive to a lot of different parameters. For example, total matter density, the amplitude fluctuations, which for low redshift, we usually phrase in terms of this sigma 8 parameter. It's also sensitive to neutrino mass, you know, varying dark energy equation of state and things like that, right? Based on this equation I've shown you earlier, all of these things enter. Okay, let me just quickly go over the advantages and disadvantages of weak lensing. So first of all, the advantage, one big advantage is sensitive to the total matter. Okay, total matter is dominated by the dark matter. We think we have very good models of dark matter in terms of M-body simulation, stuff like that. So in terms of modeling, this is much cleaner than the other probe I'll talk about, which is galaxy clustering. However, it measures this in projection essentially. That means it's a two-dimensional map rather than three-dimensional map. So we lose a lot of information this way. And then there's a whole bunch of systematics that, you know, some of which people are very concerned about. One of them is what we call intrinsic alignment, basically that the galaxies can be correlated in their shapes, not due to the lensing, but due to some, you know, joint origin of physical origin of the shapes. Then there are baryonic effects. As I said, we're probing total matter. total matter is dominated by dark matter, but not completely. There's also baryons, and baryons do affect things a lot on small scales. Then another thing that has shown up recently in the HSC analysis is that we don't really know how to properly calibrate the redshift of the source galaxies. The photometric redshifts are not working as well as we thought they were. Then finally, there are shear calibrations. We observe something like ellipticity. How do we translate it into shear and so on? Okay, so there's a whole bunch of these systematics, which I believe they can be addressed, but it will take time. Finally, I want to stress, and I will keep stressing this point, there is one particular probe of weak lensing, which is weak lensing of cosmic micro background anisotropies, that pretty much doesn't suffer from any of these problems here. And as such, basically weak lensing of or lensing of cosmic micro background is emerging as, in some sense, the most reliable and most robust probe of large-scale structure. Okay, so let me talk about this second probe, which is galaxy clustering. Here we are looking at the galaxies and how much they cluster, but we do this in 3D. Okay, so first of all, these effects are very large. You can see by eye that the galaxies are clustered. Here I'm showing two different types of galaxies: main galaxies and red galaxies. When we go and measure their correlation function or power second, we immediately see there's a huge difference in the clustering. So clustering itself is not telling us anything about the amplitude fluctuations. We need to go beyond just the spherically averaged monopole clustering of the galaxies. And the problem is this is a problem, this biasing. Basically, how the galaxies form, where they form, it affects the amplitude of this clustering. Okay. So can we get around this, and can we learn about the amplitude of fluctuations from the galaxy clustering? The answer is yes, and this is by looking at the clustering in what we call redshift space. So in redshift space, what happens is that the galaxies are displaced by peculiar velocities due to the Doppler effect, and so this is VP here. And so instead of having clustering which is isotropic, it becomes squashed like this. This squashing actually is directly probing the velocity, and velocities are probing directly the total matter of the total matter, and this is how we can learn about the amplitude of the dark matter fluctuations. Okay, I won't go into details, but I will quickly point out that this is true on large scales, and we have very nice formulas on large scales how we can extract this amplitude of fluctuations. However, there is also another effect which is called, sometimes called fingers of God or virialization effect. So basic galaxies on small scales, they're virialized, and they also have a very large Doppler velocities, and therefore very large Doppler shifts. And then this shows up in this kind of distorted contours of isodensity contours that I'm showing here. But the bottom line is this effect is very large. These nonlinear effects are very large, and they therefore need to be modeled. All right, so what are the advantages and disadvantages of RSD? Well, the advantage is that we're sensitive to velocities, and therefore we can measure dark matter clustering. Another advantage is that we have 3D data, and means we have a lot of information, but there are systematics. We have to model biasing and nonlinear biasing, and more importantly, perhaps, we have to model what these fingers of God peculiar velocities are doing on small scales. So as a result, as I'll show, different models give actually different results. Here, I just want to show you how this modeling goes. This is for DR12 analysis for SDSS. This is a monopole, this is a quadrupole, this is a hexadecapole. You see the models actually reproduce the data pretty well, but the models have a lot of free parameters. Okay, so what is more important is, do the models agree with each other? And here the answer is not clear. First of all, so this is basically these amplitude of fluctuations. The solid gray line here is Planck. And now, first of all, you see some of these results agree very well with Planck. For example, our own result is these 2 points here. They agree very well. But what we did, for example, we also did analysis to K of 0.2 and K of 0.4. We don't know a priori up to what scale we should trust our models. Okay, and you see there's some, maybe not completely negligible shifts in our parameters, depending if we are conservative and we keep large scales, and if we are aggressive and go to small scales. Personally, I would therefore trust more the results which are less aggressive and keep the large scales. But the other thing you will notice, these measurements are all pretty much based on the same data. These are all SDSS data, and they there's a large variety. There are claims in the literature that the amplitude is low from this kind of measurement, but they're also, in complete disagreement with other measurements which claim that no, everything is consistent with Planck. So we still have a lot of modeling uncertainty here, and a lot of modeling issues that we have to address. My own conclusion from this would be it's too early to claim that the amplitude is low from these kind of measurements. Okay, so there are other things like cross correlations that pretty much follow the same thing. For example, here I'm just showing a recent compilation from Chen et al. Of these, how everything in large-scale structure is low. I would say this is a very selective choice of the experiments here, but nevertheless, in this paper they conclude they are very low. Their analysis is very low. But what I want to emphasize is the same reanalysis of the same data from Singh et al. Also gets a much higher answer, right? So again, we have a modeling uncertainty issues that we need to address. Okay, but CMB lensing comes to the rescue. This year, there was I would say, a fantastic analysis of ACT data. And we here's a compilation of these results. Basically, and here they point out that it's true that weak lensing, all of experiments are low in the amplitude, but the ACT measurement is actually perfectly consistent with Planck on this S8 or sigma 8. Okay, so and again, I want to emphasize that CMB lensing is much cleaner. Okay, has much fewer systematic issues. So I think this is a very interesting result. Okay, let me now, in the last few minutes, talk about the future. The future is very bright because we have so many of these new experiments coming up, right? Euclid has just been launched. DESI has already started taking data. Rubin Observatory will be online, in the next few years. Spherex is another satellite. Simon's Observatory is being built. South Pole Telescope is already taking data, and then there will be CMBS-4 that we'll hear about from Eric, and Lightbird. Okay, so there's a lot of experiments that are happening, or surveys, I should say. And they divide themselves into, well, large-scale structure and CMB. And okay, so CMBS-4 is the flagship for the next generation. But in terms of large-scale structure, we can divide them into photometric and spectroscopic surveys, right? Rubin is a photometric survey, whereas DESI, which has already started taking data, is a spectroscopic survey and will focus more on the redshift space distortions, whereas this one will focus more on the weak lensing side. So now, finally, in the remaining few minutes, I want to emphasize that we are getting not only new surveys, new data, we are also developing new algorithms and new methods to analyze. And I really want to emphasize this because I believe we're going to gain a lot from this. Some of these are machine learning based. And the key idea is here that, especially when we talk about large-scale structure, it's very nonlinear. And the standard statistics, such as power spectrum, they don't extract all the information from it. So we need to go beyond just the power spectrum. And there have been a lot of different statistics introduced to do that, high order correlations, clusters, peaks, a lot of them. However, what has been, thank you. What some of these recent machine learning methods have been emphasizing is that we can actually extract all the information there is using a so-called implicit likelihood, which I'll say more about it in the next few slides. And these methods have a promise to have a huge information gain. Okay, in parallel to this, there are also so-called explicit likelihood methods, where you just try to do a full forward model of either gravitational lensing effect on the CMB, for example, or perhaps the full galaxy clustering full forward model, and you try to do this kind of analysis. This requires a massive sampling in billions, millions, or billions of dimensions, and so it's computationally very challenging. It has its own challenges, but this is also something where we have made a lot of progress. Okay, I just want to quickly mention something that we recently did, so-called multi-scale flow, where you decompose, for example, weak lensing data into several different resolutions, and you try to learn the likelihood of the data at every resolution level. Okay, I won't go into details, but I just want to say this enables you to do the likelihood analysis. Moreover, it enables you to do the likelihood analysis at different scales, and you can therefore test the consistency of different scales. Here, I'm just showing the fact that when we test this on, for example, 25 models, The true answer is always within 1 or 2 sigma of our posterior. So this is a well-calibrated method. But what is perhaps more interesting is this allows you also to learn for unknown unknowns. And so as an example here, we have thrown in baryonic effects into these weak lensing maps, even though the weak lensing maps have not trained on baryonic effects. And we ask, can we detect baryonic effects? And there are 2 ways to detect them. We tried two different ways. One was just to look at scale dependence. And we see that there are some deviations on very small scales. That's because baryonic effects are predominantly on small scales. But the other one that we looked at is basically look at the density estimation and see if the density estimator itself is an anomaly. You can think of this as a generalization of a chi-square test. And both of these tests actually appear to give pretty good information about these anomalies. Okay, I won't say more about this, but I want to just tell you the bottom line of these methods. These methods are about a factor of 5 better in figure of merit, and this figure of merit is defined by omega matter sigma 8 plane. It's about factor of 5 better than power spectrum, and about a factor of 3 better than any previous other method, such as convolutional neural networks and so on, or scattering transform. So we think these methods have a lot of promise, and in fact, recently we have also tried these on tomographic beams in preparation for our analysis of hypersupreme cam data. I won't go into details, but I want to just point out that we get a massive improvement in terms of information. This is again omega matter S8 plane, and we have almost a factor of 10 improvement in terms of figure of merit relative to the power spectrum analysis. So these methods really are very promising because essentially, a factor of 10 means a factor of 10 larger, effective factor of 10 larger survey size. Okay, so, and finally, as an example of this explicit likelihood analysis, I want to show you results that we have been obtaining from analysis of cosmic background lensing, gravitational lensing. So far, all of the lensing analyses have used so-called quadratic estimators or optimal quadratic estimators. Okay, they give errors that is shown here in blue. All right, now, if you have very low noise data, and this is not yet applicable to the ACT data I was showing you, but this is going to be, it is already applicable to the SPT data, South Pole Telescope data, and for sure it will be applicable to the CMBS4 data. In that case, you can do something better than quadratic estimator. You can do a full likelihood analysis, full explicit likelihood analysis, and we get results on our simulated data. We get results which are like this. It's a factor of 2.5 improvement in terms of the amplitude relative to the quadratic estimator. So these kind of methods are also very promising and will do a lot to improve our results. Okay, so let me summarize. So Lambda CDM is the current standard model of our universe and currently explains all the data. And when I say Lambda CDM, I mean, no additional bells and whistles, 5, 6 parameters. I would argue these new recent results, especially from ACT, they do not support any evidence for the tension, either in the Hubble tension sector or in the amplitude sigma 8 tension. So obviously this is just one experiment, but I like the results because I think they're so clean, right? It's actually very difficult to point to a specific systematic in that data. Next generation surveys are coming online soon. DESI, Euclid, Rubin, Simon's Observer, and so on. So we'll have a lot more data. And finally, next generation of analysis are being developed, and in some cases, they really also massively improve on our accuracy, up to an order of magnitude increase in terms of data volume. And so I think that is also going to be an exciting development that will give us a lot more clue about what's going on. Okay, I'll stop here. Thanks.